What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 7, Section 1, Angles. Let's do it. So for number 1, it says draw an angle in standard position, label the vertex, initial side, and terminal side. So if this is our XY axis, we could say our initial side is going to be right here because we're always kind of starting in this position. And then we're going to move up to the terminal side of the angle. And these two, the terminal and the initial, form the actual angle. And then last but not least, when we're talking about the vertex is this center point in here, which is the origin. And that's how you do it. Boom, done. State what a positive or negative angle signifies and explain how to draw each. So let's look at two examples. Let's look at 30 degrees and let's look at negative 30 degrees. And let's look at how both of these might be drawn. So first, we're always going to start at this side, right? We're starting at our initial side. And if we have a positive 30 degrees, we're going in the counterclockwise direction. So we're sort of going to go up 30 like this. And then here would be our positive 30 degree angle. When we talk about negative 30, it just means starting at that same initial side, we go the same 30 degree distance, but we go clockwise now. So now we go this way, and this down here would be the negative 30. So that's the difference. Boom, done. Explain the difference between linear speed and angular speed when describing motion on a circular path. So let's say we're here. If we're talking linear speed, it's literally that distance that is being traveled divided by the amount of time, right? So it's that actual distance along that circumference. When we talk about angular speed, it's talking about what is the length of the angle traversed, right? So let's say this angle might be 115 degrees, let's say approximately. So this would be 115 degrees in how much time, right? So now it's degrees per minute or time unit. So that's the difference, done. So for this one, we're meant to draw a 300 degree angle in standard position. So again, we always start here on the initial side, and since it's positive, we're going counterclockwise. So we can go step by step. We can go first here, that's 90, right? Then we turn another quarter, that's another 90, which is 180. Then another 90, which is 270. And then we have a remaining 30 that we're going to go. So let's say 30 degrees is like about here. It's about a third of that distance. So now I can say here's my initial side, here's my terminal side, and this full thing here is our angle, and that's how you do it. Boom, done. So for this one, to draw in positive 135, again, we always start here with our initial point, and then we go 135 degrees. So first, this going up here would be 90 degrees, that nice quarter turn. And then we have a remaining 45 degrees to travel. So that's kind of right in the middle of going a full 90. So again, here's our initial side. Here would be our terminal side. And this whole piece in here is our angle at 135. Boom, done. For this one, we're talking about radians. And sometimes that might be a little bit trickier for people. But what you might remember is that this full amount going here, 180 degrees, that's the same as pi. So since this isn't pi, this is 2/3 pi, you can think of 2/3 of this full distance. Another way to think about this is to convert it to degrees. Sometimes that's easier. So 2 pi over 3 to convert to degrees, you multiply by 180 over pi. That would cancel out. 180 divided by 3 is 60 times 2 is 120 degrees. So this might be easier as well. So if you look at it now, we'd go up here, which is 90 degrees, and then you have another 30 remaining, so that might be like to here, right? And this also looks like 2/3 of pi, or 2/3 of 180. So now our final measurement would be here with our initial side, here with our terminal side, and this portion here being that angle of 2 pi thirds, or 120 degrees, boom, done. So for this one, 5 pi 6, it's again 5/6 of pi, and pi is 180. Pi is this amount. So it would be 5/6 of that distance if you want to think about it that way. Another way, which I do like, is also to convert this to degrees. So we do 5 pi over 6 times 180 over pi. The pi's cancel out. 180 divided by 6 is 30 times 5 is 150 degrees. So if we think about it from that perspective, here we go 90 degrees, and then we have 60 left over. So then another 60, right? So somewhere around here. So here is the initial side, here is the terminal side, and this measurement in here is the angle, and we'll keep it in radians of 5 pi over 6, done. So for this one, it's negative pi over 10. So now instead of going counterclockwise, we're going to go clockwise. And let's convert this to degrees. I think it might be a little easier. So pi over 10 times 180 over pi. Those cancel out. 180 divided by 10 is 18. And again, it's negative. So negative 18 degrees. We know this full amount is 90. 18 is 1/5 of that. So maybe we're going to go like starting here, maybe like this amount. So then here's the initial side. Here is the terminal side. And then here's our little angle of negative 18 or negative pi over 10 in radians. Boom, done. For this one with negative 120, again, we're going to start here as per usual. And then since it's negative, we're going clockwise. We're going this way. So here would be to 90, right? And then we have another 30 to go, so another 30 like this perhaps. So here is our initial side, here is our terminal side, and then this is that full angle of negative 120 degrees, done. So for this one, I'm going to convert it actually to degrees. I think it's going to make a lot more sense. So we got 22 pi thirds times 180 over pi. The pi's cancel out. 180 divided by 3 is 60. Times 22 is 1320 degrees. So let's figure out what this looks like because this is more than 360. So that's a little different. So again, starting here, first we would go, a full 360. So we're going all the way around. So there's 360. But then this is bigger than 360. So let's go another 360. Let's go all the way around again. So now we're up to 720. Let's go around again. Now we're up to 1080, but we still have another 240 degrees to go to get to 320. So now with that final 240, I'm going to go 90, 180, and then I've got 60 left. So we're going to go another 60, which will be right about here. So that gives our initial side here and our terminal side like this. And all of that kind of shows that angle of 22 pi over 3. And that's how you do it. Done. For this one, we've got negative, meaning we're going clockwise, and negative 4 pi thirds. Let's convert that to degrees just to make it a little easier. So I'm multiplying by 180 over pi to do so. Those cancel out. 180 divided by 3 is 60 times negative 4 is negative 240. So starting here as per usual, first, I'm going to go to the clockwise direction of 90, then another 90, that's 180, and then we have 60 left. So going 60 more would be like right around here. So here would be my initial side, here would be my terminal side, and this whole chunk here is that angle of negative 4 pi thirds, boom, done. So for this one, it says find the area of the sector, and the way we do area of a sector is the central angle, which is 140 here, divided by 360 times the area of the entire circle, which can be found by pi r squared, and here r is 3. So they want us to round to 2 decimal places, so let's plug it into Desmos. So what we get is 10.995, which is actually going to round up to 11.00, and this is in inches for the radius, so it's going to be inches squared because it's area. That's how you do it. Done. So for this question, it says to find the area of the sector, and to do area of a sector, what you do is you do the measure of the central angle, which in this case is in radians. So we take that and we divide it by the total amount of radians in a circle going all the way around, which is 2 pi, right? If we were in degrees, it'd be this over 360. And then it's times the area of the entire circle, which is pi, times the radius, in this case 4.5, and that value squared. All right, let's plug it into Desmos and see what we get. So here we get the full value, which approximately becomes 12.72. So the area is rounded to the nearest hundredth, 12.72 centimeters squared. Boom, done. For this question, we're converting radians to degrees, and the way you do that is you take your measure in radians and you multiply it by 180 over pi. And this makes sense because 180 degrees is equivalent to pi radians. So that's why we have this ratio. Now as we multiply across, we cancel out the pi's, and then it's 180 over 9, which simplifies to 20. So it's equivalent to 20 degrees, done. So to convert this, we take the measure in radians and multiply by 180 over pi. So you can do that with any angle measure in radians to convert to degrees. So then the pi's cancel out, 180 over 3, which becomes 60. So that's 60 degrees, done. So to convert to degrees, I'm going to take this in radians and we're going to multiply by 180 over pi like so. The pi's will cancel out. And now we can multiply across. Negative 5 times 180 is negative 900 divided by 12. And that goes in 75 times. So that's negative 75 degrees, done. So for this one, we're converting degrees to radians. And what we're going to do is now, like in the other conversions, when we're going radians to degrees, you multiply by 180 over pi. But here, we multiply by the reciprocal, right? We're going from degrees to radians. So it's times pi over 180. Now, as we multiply across, we get 90 pi over 180. But we can simplify. We can divide top and bottom by 90, right? 90 divided by 90 is 1. That's 2. So then this becomes 1 pi over 2. That's how you do it. Done. To convert this one, we multiply negative 540 times pi over 180. That's how you convert degrees to radians. So I can divide the top and bottom by 180 actually, and that goes in once. Here it goes in 3 times, but since it's a negative, negative 3, then we multiply across and we get negative 3 pi over 1, which is just negative 3 pi. Boom. So for this one, we're going to take the degree measure, put it over 1, and multiply by pi over 180. That's how you always convert degrees to radians. But look at this. The 180s can cancel out on the top and bottom, and we're left with just pi. So 180 degrees is pi radians. Done. So to convert this one, we take 150, and we multiply it by pi over 180. Now, the top and bottom, 150 and 180 can both be divided by 30. 150 divided by 30 is 5. 180 divided by 30 is 6. So then we have 5 pi on top for the numerator as they multiply across, divided by 6. So there's your measure in radians. Done. So here we're meant to find the length of an arc of a circle with that radius and this central angle. So the formula for length of an arc is the central angle, which in this case is pi thirds, divided by 2 pi. That's because we're in radians. And then it's times the circumference of the circle, which is 2 times pi times the radius 5.02. So let's plug it into Desmos and approximate. And when you plug everything in, we get 5.26 rounded to the nearest hundredth. So that is 5.26 miles approximately. Boom, done. Here we're going to find the length of an arc with radius 10 and central angle of 50. So the way we find length is we first take that central angle and we put it over, since we're in degrees, 360. And then it's times the circumference of the circle. So circumference is 2 times pi times the radius, which is 10. So let's plug it into Desmos and see what we get. So here we get 8.73 to the nearest hundredth. So the length would be 8.73 centimeters. Boom, done. So this one, we're doing arc length, which is central angle 63 divided by the total degrees in a circle, which is 360. And then times the circumference, which is 2 times pi times the radius, which is half of that diameter. So if it's 12, that's going to be 6. Now let's plug and chug in the calculator. And here we get 6.597, which rounds up to 6.60. So we'll say 6.60 meters. Boom, done. So to find the area of the sector, we take the central angle divided by 360, the total degrees going all the way around the circle, and then times the area of the circle. And area is pi times radius squared. And in this case, the radius is 20. So let's plug and chug in the calculator and see what we get. So here we get 104.7198. So approximately 104.7198 centimeters squared. Boom. So here to get the area, we take the central angle, and in this case, it's in radians. And so now we divide by 2 pi. If it was degrees, we'd be dividing by 360, but it's basically, that's the amount of radians going all the way around a circle. Just like in degrees, it would be 360. And then times the area of the circle, which is pi times radius squared. And here the radius is 0.7. So let's plug this into Desmos and we'll see what we get. So here we get 0.7697. So that would be 0.7697. And since it's inches here, it's inches squared. Boom, done. So here we're meant to find a coterminal angle that's between 0 and 360. So the way we find coterminal angles is we just add or subtract by 360. Those will give you all the possible coterminal angles. So I'm going to start by adding by 360 because I know I want to get a positive value. So when I do negative 110 plus 360, we get positive 250. Well, this is coterminal and it's between 0 and 360. So that's it. We're done. There's the answer. So to find a coterminal angle, I'm either going to add by 360 or subtract by 360. And since I'm above that 0 to 360 angle measurement, I'm going to subtract. So we're going to first subtract by 360 and I get 1040. That's still too big. That's still bigger than what we want. So I'm going to subtract by 360 again, and we get 680, but that's still too big. So let's subtract by 360 again, and now we get to 320 degrees. Guess what? That's between 0 and 360. That's coterminal with 1400. So there's the answer. Done. So for this one, when we're finding coterminal between 0 and 2 pi, it's very similar to degrees. When we're talking about degrees, we're adding or subtracting by 360. That's the amount of degrees to go all the way around in a circle. Well, in radians, that equivalent value is 2 pi. So I'm going to either be adding or subtracting by multiples of 2 pi to get this into that right zone. Now, this is a little more than 3 pi. So right now, this is too big. So what we're going to have to do is we're going to subtract by 2 pi or multiples of 2 pi. So first, let's subtract by 2 pi. Problem is we need common denominators. So I'm going to multiply the top and bottom by 3. So this becomes 6 pi over 3. 10 pi minus 6 pi is 4 pi over 3. That is between 0 and 2 pi. So there you go. Done. So for this one, to get it between 0 and 2 pi, we have to subtract by multiples of 2 pi. And, or it might be adding, but you can see it's much bigger than 2 pi, so we have to subtract. And to get a common denominator of 9, I'm going to be subtracting by 18 pi over 9. So after we do the first subtraction, it's going to be 26 pi over 9. And again, that's still bigger than 2 pi because 2 pi would be 18 pi over 9. So we have to subtract again. 26 minus 18 is 8, so now we get 8 pi over 9. That's how you do it. Done. So this says a bike with a 24-inch diameter is traveling at 15 miles per hour. Find the angular speed of the wheels in radians per minute. So if it's 24-inch diameter, it means it's 12 inches for the radius, which is the same as 1 foot. So we're going to start by figuring out the circumference of this guy. And again, we've got it in feet. This is in miles. So we'll calculate that in feet, and that's going to be 2 times pi times the radius, which is 1. So it's just going to be 2 pi. And then to convert 15 miles to feet, we do 15 times 5,280. And that's 79,200. So in 1 hour, we're going 79,200 feet. And to get the number of revolutions in that hour, or 60 minutes, we're going to divide by the circumference, which is 2 pi. So let's do that in Desmos. So we get 12,605, and that's the number of revolutions. So this is the number of revolutions, and the cool thing is to go back to the amount of radians it's going in this amount of time. We're just going to, again, the number of revolutions times 2 pi is 2 pi is 1 full revolution. So this essentially goes back to 79,200. And that's the amount of radians. And now we're trying to figure out how many radians per minute. Well, this is in an hour, so this is per 60 minutes. So when we divide by 60, we get our angular speed of 1320 radians per minute. Now, if we want revolutions per minute, this was our number of revolutions, if you guys remember that correctly. So we just take that and we divide that by 60. Okay, let's see in Desmos. So we take this and we get 210.085 rounded to the nearest thousandth. So it's 210.085 revolutions per minute. And that's how you do it. Boom, done. A wheel of radius 14 inches is rotating at 0.5 radians per second. What is the linear speed, the angular speed, and the angular speed? And so this is in revolutions per minute and degrees per second. So first, let's get the angular speed in degrees per second because we already have that. It's just 0.5 radians per 1 second. And how do we convert radians to degrees? We multiply by 180 over pi, and this equals 90 divided by pi, which approximates to 28.65. So that's the angular speed in degrees per second. Now to get the angular speed in revolutions per minute, 1 revolution, if we're talking about radians, is going 2 pi. So if we start out with 0.5 radians per 1 second and we're converting radians to revolutions, we know that 1 revolution is equal to 2 pi radians. So this would give us 0.5 divided by 2 pi. And this gives us approximately 0.0795. And this is now revolutions, but we're still in seconds because they want this in minutes. So to get this into minutes, we need 1 minute to be the new time unit. And then we have to convert away from seconds. So how many seconds is equal to 1 minute? 60 seconds. So these will cancel out, and then I do this times 60. And this gives me roughly 4.77. So that is angular speed is 4.77 revolutions per minute. And last but not least, we're going to get that linear speed, which is going to be in inches per second. So to do this most effectively and efficiently, I'm going to go back to the revolutions per second. So we know that it's 0.07958 revolutions per 1 second. And now I can convert a revolution to inches because 1 revolution is equal to the circumference. And what's the circumference? It's 2 times pi times the radius, which is 14. So let's now plug this into Desmos. Let's see what we get. And when you multiply it out, look at that. We get exactly 7. So that linear speed is going to be 7 inches per second. So here are all of your answers. Boom, done. So for this question, it's starting by giving us this information that when we're writing, we've got a speed of 4,800 revolutions per minute. And we're trying to turn this into linear speed in terms of millimeters per second. So we're trying to turn this into a linear speed of meters per second. So first, if that diameter is 120, we know that this is going to be 60 millimeters, which if we do it in meters, we're going to move the decimal over 1, 2, 3 times. So that's 0.06 meters. So first we have revolutions per minute. Now first I'll convert it to millimeters per minute because they do have that in the answer. Now here's the dealio, right? 1 revolution, that's what we need to convert away from, is equal to 1 go around, which is 1 of the circumference, which in millimeters is 2 times pi times the radius. So now we can calculate this and get our nice millimeters per minute. So let's do that in Desmos. And we get 1,809,557.37. And now if we want to do meters per second, we can kind of continue on with this and say 4,800 revolutions per, and I can just convert that minutes right away to 60 seconds. We can say per 60 seconds. And then again, we're converting revolutions to meters. So 1 revolution is the same as the circumference, but in meters is 2 times pi times the radius in meters, which is 0.06. So now let's plug this into Desmos and see what that gives us. And we get 30.16 to the nearest hundredth, which is 30.16 meters per second. So that's how you do it. Boom, done. Find the distance along an arc on the surface of the Earth that subtends a central angle of 5 minutes. So what we're going to do is we're going to take that central angle, and it's basically saying 1 minute is 1/60th, so 5 minutes would be 5/60ths or 1/12th of a degree. And we divide that by the total amount of degrees going around in a circle, which is 360, times the circumference of the Earth, which would be 2 times pi times the radius, which is 3960. So now let's plug it into Desmos. And we get approximately 5.76 if you round it to the nearest hundredth. So it would be roughly 5.76 miles. Boom, done. So this question asks, how far does the minute hand travel in 20 minutes in terms of degrees? So if we look at a clock, right, this is just a quick drawing. That's 12, that's 1, that's 2, that's 3, that is 4, 5, like this. So you can see, of course, this is 180 degrees, 360 is going all the way around, right? And so what does this split up into, right? If this is 180 and it's split up into 6 pieces, okay, 180 divided by 6 is 30. So each one of these little sections is 30 degrees, 30 degrees, 30 degrees, right? And also, since each one of these little paths is 5 minutes, right? 5, 10, 15, 20, that's going 4 of these lengths, which is 4 times 30, which is 120 degrees. Boom, done. So this question says the city is located 40 degrees north latitude. Assume the radius is this, and the Earth rotates once every 24 hours. Find the linear speed. So first, what are we talking about when they say 40 degrees north latitude? That means that if this is the equator going straight across, 40 degrees north latitude would be like this, meaning this would be a 40-degree angle. And what we're trying to figure out is we're trying to figure out the circumference at this point as it kind of goes around and rotates around like that. So in order to figure out the circumference there, I need to kind of know this sort of radius of this little circle that would be cut out from the top here. So the way we can figure that out is to make another triangle right on top of this. And I'm going to show you why this works, because this is a really nice right triangle, and I already know that this is the radius here. And they've given us that the radius is 3,960 miles. And since this is 40 degrees here, this is 40 here. These two are parallel, so those are alternate interior angles. This is 50. So now using some trig, we have enough information to figure out the length of this line. So check it out. I'm going to say cosine of 40 equals adjacent, which is the side we want to solve for, equals adjacent over the hypotenuse, which we know is 3960. Then I'm going to multiply both sides by 3960. And this is our value for this radius up here. And now we can figure out the circumference, because circumference is 2 pi times radius, which is this value. And then this will give us that full circumference in miles, and we need to go miles per hour. So this is in 24 hours, so we divide by 24. Let's see what we get in Desmos. So as we plug it in, we get approximately 794. So the answer is 794 miles per hour. Boom, done. Find the linear speed of the moon if the average distance between the Earth and the moon is 239,000 miles, assuming the orbit of the moon is circular and requires 28 days. So if we have Earth here and we have the moon here, what they're saying is that this is a distance of 239,000, and the moon then is going to orbit the Earth like so in a perfect circle. So what this means is we can calculate the distance traveled in miles and then divide by the number of hours there are in 28 days. So the distance traveled going all the way around is that circumference, which is 2 pi and then times the radius. And then what we're doing to get this in miles per hour, this is in days, so we have to divide by the number of hours, which is 28 days times 24 hours per day. So this is what we can use to get our solution. Let's plug it into Desmos. And here we get approximately 2,234. And they didn't round up in the back of the book, though it does look like we should probably round up. So I'm going to say 2235. So we'll say 2235 miles per hour. Boom, done. A car travels 3 miles and the tires make this many revolutions. What is the radius of a tire in inches? So first we imagine a tire having some sort of a radius here. And the circumference of this tire is 2 pi times the radius. Now we want to take this value, this circumference, 2 pi r, and we're doing it, we're traveling that distance, that circumference this many times, 2,640 times, and we want this to equal 3 miles. But the thing is, our radius is in inches, so we need this mile value in inches as well. So to convert 3 miles to inches, first we convert it to feet by multiplying by 5,280. And then since there's 12 inches in a foot, we multiply it again by 12. So now on the left side, we have 5,280 pi radius equals 3 times 5,280 times 12, which equals 190,080. Last step to solve for radius, we're going to divide both sides by 5,280 pi. And we're going to plug it into Desmos. And we get approximately 11.5 as we round up to the nearest tenth. So the radius would be approximately 11.5 inches. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.